Okay, so I just turned on the recording. All right, so yeah, it's the last class. So I guess we have 3 presentations today. Did anyone have any comments or questions about this week's content before we go to the presentations?
I had I guess a couple quick questions about it.
Yeah.
So with the learning graphs, but I guess first broad question, why is it called a learning graph?
Yeah. Huh. It's not a great name. So it's called the learning graph. Because that's what it was called in the first paper, I guess, that talked about it. But broadly speaking, it describes the order in which you learn the bits of the input. So it's like a graph that describes, how you're going to learn the certificate roughly. So yeah.
And then on that, how does one, generally speaking, I guess choose, like what would be good guiding principles for making a learning graph bound? Because both of the ones kind of seem like you need pretty strong insights into how you're going to try to solve the problem.
Yeah, well, so I mean, the learning graphs are more about, searching for a certificate. Right. So, the one example we saw that was kind of a bit more complicated was for element distinctness, where you were reading a random set of R bits first before reading the right bits, and that turned out to be a better strategy than just directly reading the right bits, I guess, for the quantum algorithm, the results. So that's one trick to try, is to just read more bits, load more bits first before kind of going to the right one and branching out at random before kind of converging to the right answer. I feel like that's one of the main tricks that the learning graphs let you do kind of easily. Of course, if your problem has more structure, so you condition on one bit, then you will change where you would search for a certificate. Then of course you can encode that too, right? You can say, okay, let's read this one first, and then fork to read this other one, one of these other ones. But generally, I'm not sure if there's like a lot of ideas or tricks out there for how to use a learning graph. So there's a few more papers that. There's a paper that does things like K-sum or K-distinctness using learning graphs, and so we'll take up one of those. There's part of the story is that it hasn't been used that many times. Each time it's used, maybe another trick or another way of using it is introduced, but it's not like a very a deeply developed field. And then it is limited. It's not equal to quantum query complexity, in part because it can sort of only depend on where the certificates are positionally, like which entries they are in the input, but not really, what the certificate is. Like, it's sort of you when you describe your learning graph, you're describing what you read, and then depending on the input, you can have a flow on this graph. But you can't really, in the original graph, have a branch that depends on the value of the bit that you read. So you can't really branch, like you say, okay, let's read bit number 1, but you can't then branch and say, if it was 0, read something else, read bit 2, and if it was 1, read bit 5. You can't describe that in the original graph. you can, to a limited extent, describe that in a flow, but only for the 1 inputs, not for the 0 inputs. So it's kind of, it's kind of limited, and it usually gives tight quantum algorithms in the case where you're really making some kind of black box search, or you're just looking for a certificate in a needle in a haystack kind of thing, and there's not a lot of deep structure. When there is more deep structure in your problem, then it's a bit hard to encode it in a learning graph, and sometimes it's impossible. Whereas the negative weight quantum adversary is of course general enough to be equal to quantum query complexity. So but it's sort of, it's a bit, it can be a bit trickier to use. The learning graph often kind of guides you to the right. I mean, I don't know exactly. It tells you a bit more where to look for things, or how to try to construct something. Whereas the negative weight adversary bound leaves you on your own to kind of figure out what's up with your specific problem and how to attack it. Yeah.
I mean, it's kind of a middle step between an algorithm and a bound, it seems.
The negative weight adversary.
No, the learning graph. Sorry, in that, like, it gives you a procedure that you could use. It's not fully at the point where it's an algorithm, but it's close.
Yeah, it feels a bit more algorithmic, I suppose. Yeah. I mean, once you get the hang of what the negative weight adversary bound is, what learning graphs are doing, how you convert learning graphs to negative weight adversary bounds, it's a little tricky, but once you get the hang of it, it's kind of only using the same kind of indexing trick where things you've read before are used to index positions in your long vectors. And this is a very common trick to use when you design a negative weight adversary bound. I don't know. I think when you internalize that trick, then the negative weight adversary bound can also feel algorithmic, I guess is what I'm trying to say. But,
okay.
But less so, I guess, than the learning graph. Yeah. All right. Well, let's actually, any other comments? So if not, let's go to the presentations. So here. So there were 3 of them. We have Zhangfei, Olivier, and Andrew.
I can go first if no one else wants to go.
Okay,
that's good with me.
Okay, great. Let me pull everything up. It's Olivier, by the way. So can everyone see my screen?
Yep, and we can hear you, and we can see the mouse.
Oh, great. Okay, that's fine. Okay, that's working. Okay, hey everyone. Today, I'll be walking everyone through this paper called Improved Quantum Query Algorithms for Triangle Finding and Associativity Testing by Lee et al. So let's get started. So everyone knows what query complexity is, of course, quantum query complexity. So triangle detection. So triangle finding is just what it sounds like. It's finding triangles in a graph. And so how would you do that in a kind of query sense. So you'd make queries of the form, is there an edge between vertex I and vertex J, and then determine if a graph has a triangle based on those queries. So people have not only done this, but they've found kind of lower bounds for this problem, starting in '96, I believe, with a paper by Grover called a fast quantum mechanical algorithm for database search. So we have a lower bound there, and then again in '05 with n to the 1.3 queries. I think that paper was called Quantum Algorithms for the Triangle Problem. So that was specifically for this. And then Belob's himself, I believe this is a paper that is going to be presented, I think, where Belob's algorithm can be used for this problem. And then that would be n to the 35/27 queries. And then this paper improves this further. So associativity testing. So that's the second part here. And that's defined as given Oracle access to the multiplication table of an operation circle, query A comma B, receive C equals A round B. And that is determining if for all these triples, A round B round C equals A round B round C. Yeah, so that it's basically determining if for all triples that holds, right? Again, the same paper determined the lower bound for this to be n to the 3/2. And this paper is although
these
this
are
is
upper bound, by the way.
Oh,
so,
is an upper bound? Oh, sorry.
What you call, these are algorithms, I guess, but so we usually call them upper bounds. But yeah, like, your numbers are going down. Those are
Right.
improving upper bounds.
True.
Yeah.
Sorry about that, guys. Upper bounds. Anyways, this paper is the first improvement, although it's an older paper from 2012, I believe. The first improvement on that with n to the 10/7. So what prompted them to have this improvement over these previous algorithms? Well, Reichardt in 2010 showed that the general adversary bound, which was formerly just a lower bound technique for quantum query complexity, is also an upper bound technique, which means that it characterizes bounded error quantum query complexity. And this general adversary bound can be written as a semi-definite program. So as you can see there, so this gives a new way to design algorithms. And so they use this knowledge to use SDPs. But that ended up being pretty tough because the minimization form of the adversary bound has an exponential amount of constraints. So even for simple functions, it would have been challenging to not only write down just a feasible solution, or sorry, so just to write down a feasible solution, much less worry about finding a solution with a good objective value. So luckily for them, for what we just talked about, learning graphs were described by Belovs in his 2011 paper. And these learning graphs can be viewed as the minimization form of the general adversary bound, but with additional structure imposed on the form of the solution. So this means that the additional structure means that it makes learning graphs easier to reason about ensuring that the constraints are automatically satisfied. And since the constraints are automatically satisfied, then you can find one with a good objective value. So so although we did just say that it hasn't been used much, apparently it's been used successfully in some problems: element distinctness, triangle finding, etc. So what did they do exactly? Well, they made a language. They made their own abstract language for learning graphs. So for subgraph detection, right? So this subgraph detection, which would then be used for the triangle problem and the associativity testing. So what was cool about this high-level language is that one of their theorems, their main theorem, in fact, compiles this high-level language into a learning graph, and then bounds the complexity of this after this compilation, then bounds the complexity of the resulting quantum query algorithm. So after the theory is proven, that main theorem that I was talking about, they can design quantum query algorithms using only that high-level language without reference to learning graphs, which makes it much simpler. So this illustrates the evolution of a learning graph. So this high-level language has 3 commands: the setup, and then load a vertice and load an edge. So this is showing a loading schedule, which is the sequence of instructions: setup, load vertice, load edge. So for triangle optimality, so after that high-level language is set up, it then becomes trivial to solve this problem. So going from the Boolean alphabet to a non-Boolean alphabet, their algorithm can find subgraphs of specified edge colors in a colored graph, and this colored graph is what makes the triangle finding so easy to solve. For example, they show the triangle sum problem here, and where they label the vertices, or sorry, the edges, and it's easy to solve when you can with the high-level language. Sorry. And so for associativity testing, it's just going one step further. It's they just extend the algorithm from undirected uncolored graph to a directed colored graph, and all they need to show is that that the non-associative subgraph is not in the graph, and then it's associative, because if it is in there, then it's non-associative. So that is for the associativity testing. So, sorry, that's the talk.
All right. Thanks.
Thank you.
Any questions? So did their algorithm for the triangle sum end up being typed then, or
the triangle sum here? This one?
Sorry?
This for the triangle sum problem?
Yeah, so they're typed for that?
Yeah, I believe so.
Okay, but not for triangle finding, I guess.
Let me just double check.
I think that's right. I think. Yeah, because there's been a further improvement since, I believe, on triangle finding. Yeah,
okay.
But I mean, I guess the triangle sum has a lower bound. Yeah, triangle finding, I think, is still open. Exactly what the best algorithm is, or perhaps there's just a missing lower bound. But yeah, so I guess this also partially answers the question Lane had, which is how do you construct these learning graphs? So here they have kind of their own framework for how to construct them, but the reason why it's not necessarily a satisfying answer is that I don't know if it's been used in that much follow-up work. So that's what worked for this problem, like to use this this framework. But in follow-up work, then people construct these learning graphs in other ways, I think. So it's not that this is the standard way that is always used, but still it's something.
Right. Well, they list some problems here that where learning graphs were apparently enormously successful. But I mean, 2 of them were by Belovs himself, so maybe not the entirely representative of how successful learning graphs are.
Right. I mean, and often many things you can do with learning graphs, you can also do with quantum walks directly, but not always. Yeah. So there's some cases where constructing the learning graph is a lot easier than constructing the quantum walk. Okay, thanks. Okay, so thanks, Olivier. And who wants to go next?
I'd be happy to do it.
Sure, go ahead.
All right, can you guys see my screen?
Yes.
Yep.
And we can see it.
Awesome.
And the slides. Whoops.
Thanks,
Yeah.
Ryan.
Okay, and I guess before I begin, a question for Shalev. Is this juntas or junta? I don't know if you know the proper pronunciation.
It's juntas.
Junta? Okay.
Yeah, junta.
All right, so
they're named after this concept of a military junta, which I believe is used in English. So that's an English word for basically a dictatorship by a small number of people instead of by one person. So it's a junta. Anyway, so this concept in computer science is when a function is only dependent on a few bits, even though it has a lot of input bits. Then this function would be a junta. Anyway.
Awesome. All right. Well, at least the derivation makes sense. But so I'm talking about this paper by Belovs on quantum algorithms for learning symmetric juntas via the adversary bound. So we'll start off with the definition that Shalev was just briefly giving. So essentially what we're doing is we're looking at a function h from like a Boolean function from a set of size k to 0, 1, and we guarantee that it's symmetric. So we're given oracle access to a function f from a set of size n to 1, but it only depends on some k subset of n. And on that k subset, it acts as h. So this is a junta, but specifically with this fixed symmetric function known up front. So our goal is to determine this k subset, right? So we're allowed to query f, and we're trying to figure out which subset of the inputs are actually the important ones that f actually considers. So for a fixed k subset a, we'll define f sub a to just be the corresponding function. So for some examples that they gave in the paper, when h is the XOR function, this is just a restricted variant of the Bernstein-Vazirani problem. So the Bernstein-Vazirani problem is you'll take the dot product of some hidden vector with your inputs. And here you're essentially just taking, when you're taking the XOR, that is just the dot product mod 2 with a vector specifically of size k that, is the characteristic vector of this subset h. And then the second thing is, the second example is when h is the OR function. And this is what's known as the combinatorial group testing problem. And essentially what it does is you can query it on sets. And if you ever have an overlap with the important set A, the set that you're looking for, it'll output 1. And through those queries, you can kind of try to narrow it down. I saw this described as like using, lights and connecting wires to light bulbs to figure out which light bulbs were out in a row. So it's kind of something similar to that idea. But with that definition out of the way, we can go into some of the notation. So Belovs is kind of coming at this from a machine learning point of view, at least in this paper. So he uses two kind of important terms. The first one is a concept class. So he uses this like mathcal C to denote a concept class, which is just a fixed class of functions. So in particular here, C just corresponds with the set of k subsets of n. And for each one of those, we have this f sub a that we defined earlier. And then the thing that we're looking at is a learning problem, right? So you have this L sub h is the function, superscript n, which is the number of inputs. And it maps essentially functions of this type to the set that is being output. So this LH, the n of FA, should output A for every A in the concept class. So this learning problem is essentially, this is ideally what we want to reproduce. So when we define the quantum query complexity, we're just going to call it this Q of LHN. So another important thing is Belovs is using the adversary bound and the primal adversary bound, and his notation is just ever so slightly different than the one that we did in the course notes. So the negative weighted adversary bound of LHN is the optimal value where you maximize the spectral norm of this this gamma matrix, and you're subject to these two constraints. In the first constraint, he defines this kind of weird notation, this composed with delta sub S matrix. All that means is you're taking the rows where the set S outputs 1 and the columns where it outputs 0, or vice versa, something along those lines. But you're just looking at a submatrix of gamma. So that should have a spectral norm less than or equal to 1 for every subset. And moreover, the AA entry, so this gamma is indexed by the elements of the concept class, each of these k subsets A, and the AA entry should be 0, so it's just 0 along the diagonal. And the primal of that, something that he just alludes to and shows in a separate paper, is where you're minimizing the maximum over all of these elements of the concept class, the sum over the subsets, and then you take the XS of AA. And this XS is going to be a positive semi-definite matrix, which is this last condition at the bottom. And moreover, it satisfies this condition that whenever f sub A of S is not equal to f sub B of S, so whenever the, for some input A, or for some set A and for some hidden set B, they would differ on this set S. You're taking the submatrix, the AB entry of the submatrix, and it has to always be 1, or the sum of those has to always be 1 for every A not equal to B in the concept class. So with these definitions, basically what he wants to tackle is this problem, kind of the same problem of, the reason he developed a learning class in the first place in 2011 was simplifying the way to find primal, at least feasible primal solutions in order to provide an upper bound. And he's going about this in a different point, from a different point of view. So we'll see that with this first approach. So the first thing we wanted to show was this, show that the quantum query complexity of the OR sub k function in this kind of junta model is theta of k to the 1/2. And this had been somewhat shown before, at least bounds had been put on this before by a paper by Ambianas, where it was between k to the 1/2 and k to the 1. But here he shows definitively an upper bound of k to the 1/2 using just this, finding a feasible primal solution to this primal adversary problem. So the lower bound just comes from a reduction to unordered search. And the upper bound, as I said, is a feasible primal solution. So the way that he does this is he defines these rank 1 matrices ys of p. And p is just some probability. It ranges between 0 and 1. And as you see in the second bullet right there, we're going to end up taking the integral from 0 to 1 over all of these p. But this YSP depends on the probability of picking a subset, a specific subset of size, whatever the size of S is. So it's just P to the size of S times 1 minus P to the 1 minus S. It's just like a binomial distribution. I mean, it's a lot of lines where he goes through the justification of why this is a feasible primal solution, why these matrices XS are positive semi-definite, and why they satisfy this sum property. But it ends up being that this is a primal solution. But not really happy with that, Belov's decided that he wanted to generalize this for all problems of this type to kind of like the same way that the learning graphs do, give a sort of formulaic way of approaching finding feasible primal solutions for these types of problems. So here he gets into this general approach. So he reformulates this adversary bound for this specific concept class of symmetric functions, or these, I guess, each concept class for each in particular symmetric function. So he defines this new adversary bound, and he proves that it's equivalent. That for any symmetric function h, the negative weighted adversary bound of ln h or LHN is equal to the supremum over all lists of real numbers, and it's just the maximum real number in that list, subject to these constraints that the last real number in this list, the dk value, is 0, and for every integer m from 1 to k, for every t from 0 to k minus m, and for every probability p in 0, 1, we have a spectral norm of this matrix, and he goes through several lines of successive definitions to get this matrix, and they're based on, I think, like Krawchuk, I'm sure I'm not pronouncing that correctly, polynomials, and it comes from the field of representation theory, but he shows this specific matrix that has to have a spectral norm less than or equal to 1. And the nice thing here, though, is that we've reduced this problem of finding these matrices XS from before to this problem of finding just a list of real numbers that satisfy certain properties. And that hopefully makes it a little bit easier. So he shows this with 2 examples. The first is the exact half problem, which it outputs 1 only when exactly the floor of k over 2 elements are equal to 1 in the input. And he gives an upper bound showing that this is definitively showing that this is theta of k to the 1/4. So the lower bound comes from just a kind of simple positive weighted adversary from like the week 5 in our course notes. But the upper bound comes from a feasible primal solution to this modified adversary bound that he proved in the general case that I showed in the last slide. So what he does is he shows that it satisfies this reducibility property. That for every, k prime less than k, if you essentially find di prime equal di plus k minus k prime, so essentially you just take the rightmost k prime elements of this vector from, it was d0 up to dk, you just take the whatever up to dk, the k prime of them, and you restrict these constraints appropriately, you end up getting an optimization problem for the function h prime, which is the exact half sub k prime, and it ends up being that that satisfies the same properties. That is like the adversary bound for that problem. And therefore, you only need to maximize with respect to D0, because you end up showing that D0 must be greater than D1, must be greater than, etc., if you have an optimal solution to this problem. If you found the supremum, it will satisfy those constraints. So now we have a set of recursive constraints, and you're just optimizing, maximizing a single variable D0. And this is several pages of work, but he goes on to construct a feasible solution to the dual of this new optimization problem, and he's able to obtain this k to the 1/4 bound. And the last example he shows is on the majority function. Now, this majority function is essentially something very similar, where it's just you output 1 if the majority of the bits in this k subset are equal to 1. And again, he gives this upper bound by constructing a feasible solution. It's pretty much exactly the same approach as the exact half function, just with a new specific approach to developing this D0 term to optimizing it. However, in this case, the positive weighted adversary bound doesn't provide a tight lower bound. He shows that the positive weighted adversary gives at most a lower bound of log k. So in other words, we need to have a more advanced technique on the dual of the primal, so the original adversary bound side of things, in order to tell whether this new upper bound is tight or whether it's we can actually reduce it even further if you can find a better solution to this primal problem. And that pretty much concludes my talk.
All right, thanks. Any questions? All right, so I mean, yeah, I guess Belov's specializes this adversary bound a lot for this problem, but the first version of the adversary bound that he uses is pretty similar to the primal definition that we gave. The only difference is, the way I defined it in the notes, we have for each input and index position, we have a vector. But of course, all we're ever going to do with these vectors is take inner products of them. Sometimes we will take the inner product, sometimes we won't. But we don't really do anything else with these vectors other than take their inner products, either with themselves when you're taking the norm of the vector, or with other vectors in the same position j for some other input. So in a sense, we're not relying on the vectors themselves, but only the inner product structure of these vectors. So for each position j, we can consider the matrix of inner products, where we inner product together the vectors at position j. So yeah, this is the second definition there, the primal definition that you have in that slide. So what I'm saying is XS, the subset S, well, here in this case, we have one possible query for each subset. So the subset S is basically like the position J at which you're querying. So X sub S is basically like X sub J, where that's the query position, because you have one query for each possible subset. So yeah, and so you can form a matrix where you look at position x comma y of the matrix. You have the vector for x comma j inner product with the vector for y comma j. And so these matrices, you would have one for each position. You'd have one matrix for each j. And then they completely determine everything you need in order to describe the adversary bound, except that these matrices have to come from inner products of vectors, right? There would have to be a set of like row vectors and a set of vectors such that this matrix is the inner product matrix for that set of vectors. Like that's the matrix you get when you take inner products of these sets of vectors with themselves. But that's equivalent to saying that the matrix has to be positive semi-definite. So that's just a linear algebra fact. If you're trying to say this matrix comes from, the inner product of a set of vectors with itself, then you're just saying the matrix is positive semi-definite. So this is basically these matrices XS are those matrices. So they're positive semi-definite, and you want to take the sum over all such matrices of one diagonal of the diagonal entry at AA, like here. So here the capital A is basically an input. So imagine it was like a lowercase x or something, or a lowercase y. It's basically an input. So at position x comma x is basically inner producting the vector with itself. So that's the norm, and you're summing up these norms over all different positions. So over all the different s. And then you take the maximum over such an input. So you take the maximum over A. So that's the thing to minimize. And then the constraint is that, the constraint is written as well. So it's basically just equivalent to the constraint we had. So the only difference here is that he switched notations from talking about the vectors to talking about the positive semi-definite matrices you get from like the inner product structure of these vectors. And one reason that he's doing this switch, that it's more convenient for him to talk about these inner product matrices, is that later for the construction he integrates. I think you had it on some slides. He integrates these rank 1 matrices, and that actually corresponds in our notation to having infinitely long vectors. The vectors are basically, yeah, so these is integrating the YS matrices. But each YS matrix is a rank 1 matrix, so it's basically, it's as if you have one entry in each vector. So each vector is basically dimension 1 in the YS. So YS is like the inner product structure of vectors of dimension 1. And so if you add up 2 such matrices, it's like you increase the dimension of your vector from 1 to 2. You've basically kind of glued together 2 vectors. But here he's integrating, so that's like taking infinitely long vectors and interproducting them with each other. And in fact, it's like a continuum of, like, the dimension of his vectors is basically uncountably large. So it's pretty awkward to do in terms of explicit vectors. So instead, he switches notations to this inner product structure for these positive semi-definite matrices, and then you can just integrate them. So that's sort of what's going on there. So it gives you one kind of pretty bizarre application of the negative weight adversary band, where instead of constructing these vectors directly, you're basically implicitly constructing these infinitely long vectors. Even though we actually have a mathematical guarantee that you're not going to need more than 2 to the n dimensions, where n is the number of input bits. So we actually know you don't need infinitely long vectors ever. But for his math, or for his solution, the way he constructed this one solution, integrating was the nicer thing to do. So even though we know it's not necessary, that's sort of was the easier way to construct the solution. Yeah, I don't know. It's just kind of a bizarre way to come up with a solution to the primal problem of the negative weight adversary band. Yeah, so that's all I wanted to point out about that. Just kind of what these positive semi-definite matrices are. It's not very mysterious. It's just these inner product matrices for the vectors that we've seen in the primal solution, and then the construction. This integral is basically saying that the vectors are infinitely long. All right. So if there's no other questions, we can go to the last presentation. I guess by Drangfei.
We can't hear you, but we can see it, if that's what you're asking.
Yeah, we can't hear you. Yeah, we still don't hear anything.
Yeah, but it's super quiet, I think.
Oh. Is it better now?
Yep, that's a lot better, I think, right?
Okay.
Still sounds like he's a little far away.
Okay. So I'll start my presentation. So today I'm going to present a paper about K distinctness. it is also based on that semi-definite program of adversary bound and learning graph. I have to admit that I haven't fully understood the last part. I'll try to present from what I have understood. So let's first come to the problem definition. The K-distinctness problem is very similar to the element distinctness problem. First, we define the element distinctness problem, which is given a function. This function maps to 1 if and only if there are two elements that are equal to each other in the input variables. So similarly, we could define the K-distinctness problem, which is this function maps to 1 if and only if there are K values that are same within the input. So in this paper, it improved the previous results from n to the n to k over k plus 1 to this value. We can see that this value is close to n to the 3 over 4. So this better is indeed substantially better than this one. The brief idea still lies in the certificates. So basically, we try to find a small set of inputs such that the output is determined by this input, and this small set of input is called certificates. Or in our case, this one of the example of one certificate is k variable to the same value, which could determine that the output function to be 1. And also, we come to the definition of adversary bound, which previous presenters have mentioned. So basically, we can change the problem of designing a quantum algorithm into solving semi-definite positive programs. Basically, by this definition, we will hope to minimize this value subject to these restrictions. And for this problem, we also utilize the concept of learning graphs. So basically, given some input variables, we build a directed acyclic graph with its vertices as corresponding subsets of the input set, and we define the flow on the learning graph and the corresponding complexity of the learning graph. So there's this theorem that for the given learning graph G, there's a bounded error quantum correct algorithm with this complexity. This theorem is proved by constructing an example which fits this bound. So we could see that here's the actual example constructed. So for this vector, we could define a corresponding semi-definite matrix Y alpha, which is phi multiplied phi star, and if we sum this observable over all possible assignments and all edges, we could verify that this is indeed a valid solution, which both satisfies these two constraints. We call them so basically, based on this learning graph technique, we'll try to solve this K-distinctness problem. So in the original algorithm mentioned here, with this complexity, basically it builds a learning graph with 2 stages. So in stage 1, they load R random variables. So this R random variables should be different from the certificates that we need to use. And in stage 2, the 1 certificate variables are loaded. So basically, in this algorithm, if we calculate the corresponding complexity, we could find that an appropriate selection of R would yield this result. So so basically, how has this paper improved from this original algorithm? It used a learning graph as an inspiration. It tries to build a semi-definite positive X for the adversary bound. It is very similar to this form, but it is different in the sense that it tries to take so when assigning this value, they try to take other elements into account. So not only so basically in the original algorithm, the assignments are all the same. So we can completely ignore the actual value of the accepting vertices, and this is a symmetrical construction, and we can assume that this value is not relevant to the new loaded. It is irrelevant to the new loaded element, but in this advanced algorithm, we have to take into account the value of the newly loaded element. So basically, this new algorithm still have two stages, and in stage 1 and stage 2, they provide the following construction where W1 and W0 are values to be specified. So still, we sum up this observable semi-definite observable over all possible edges and all possible assignments to get these corresponding semi-definite matrices in this form. But so this is a preliminary version of the final solution, but this solution has a serious problem because it does not meet the restriction here. So this restriction 1b, because in the original learning graph model, restriction 1b is ensured by defining the concept of a flow. So by tracing the two different inputs, which maps to 1 and 0, and to trace where they start to differ, we could build a cut corresponding to the learning graph, which has the total sum of flow to be 1. But this concept no longer holds in this built model, because as this model tries to reduce the complexity by not loading actual values of every random variable, but they adopted a technique which tries to uncover the actual loaded variable only if so basically we know that sometimes the loaded variable could not be possibly in the selected certificate, because if it is the only variable with no other variables equal to it. So in this case, we will not try to load the actual value of this variable, but replace it with a star. So this will bring some problems when we try to calculate to meet this feasibility restriction here, because when we suddenly uncover a variable, it might bring exceptions to this original setting of flow. So in this primary preliminary solution, it has a problem for trying to meet the restriction here. But this solution, this preliminary solution, it already has the complexity analyzed here. So this this preliminary solution is basically improved on the complexity, but it failed to meet these restrictions. And regarding the last part about the final solution, it's based on this algorithm, made some adaptations, and somehow met this restriction here. But that part I haven't fully understood yet. So to sum up, basically they based on the concept of learning graph and inspired by this construction here. This paper tries to develop a corresponding model which somehow reduces this original complexity here by taking into account in each in the loading process in each step, taking into account the loaded element to assign the weights rather than assigning all the weights the same symmetrically, and thus made the improvement. Yeah, so that's all for my presentation. Thank you. And
all right. Thanks. Any questions? Yeah. So I don't. It's not. This is not a paper that I know very well, but yeah, it's I guess part of what's going on in this paper is that well, of course, he's trying to construct a quantum algorithm for k-distinctness, and it's sort of a learning graph approach, but not quite. And the author Belovs modifies the learning graph framework in order to get this. I mean, it still uses basically the negative weighted adversary bound, like even a normal learning graph. The reason it gives you a quantum algorithm is it goes through this negative weighted adversary bound, right? But here it's not quite a learning graph approach in that the final object doesn't have all the properties of a learning graph, but it still gives you a feasible solution to the primal form of the negative adversary bound, so you still get a valid quantum algorithm. And it's sort of learning graph-ish, so it's sort of a modification of the learning graph technique to still create a negative weighted adversary bound solution. And I guess I should note that it's not a tight algorithm for k-distinctness. So so we don't know actually the right query complexity for k-distinctness when k is larger than maybe 2 or 3. Then it's open. And I think this is not even the best known algorithm for large k, for k 10 or something. Then I think this is not the best known right now. Actually, I'm not sure if it is or not. Maybe it still is. Yeah, no, never mind. Maybe it's still the best known bound for all k, but it's not known to be tight. That's for sure. For more than k being 2 or 3. I don't remember if people actually improved this or not. So that's kind of an open problem that still remains, and it's all this difficulty with this learning graph modification that's going on here is not sufficient to get a solution that we can show is tight. And as usual, we don't necessarily know whether that's a problem with the lower bound or the upper bound, so we don't necessarily know whether there's a missing algorithm that's better. or whether it's hard to prove lower bounds using this negative weight adversary bound. Is just very difficult to use. There's some lower bounds for this problem that use the polynomial method, but they don't match the upper bound. So yeah, and you could try to construct quantum algorithms for this problem directly, I suppose, as well. But I guess that it's not known how to do that either. So again, it's just a k-distinguish problem, right? You have an input, and you want to know whether there are k elements that are all equal, k positions that are all equal, and the positions contain larger alphabet symbols, not just Boolean bits. Yeah, and you want to know whether there's k positions that are equal. Yeah, so it shows you there's a lot we still don't know about quantum query complexity. We don't know the quantum query complexity of simple problems like this. All right. So any other questions or comments about anything for this week, or perhaps for the course at large?
So this is the last course, and then this is it? Not seeing each other again? Or what's?
Yeah, this is the last live meeting. So you guys owe me final project reports, which are due at the end of the exam period. But we won't have a live meeting for those. Yeah. So actually, and I'm not going to post those. So I will just read them and grade them and perhaps give you feedback on them. But I will not post your reports. Yeah, so I guess maybe one thing I wanted to mention is I was originally talking about an assignment, which I haven't posted. I will see if I can, so it depends on whether I manage to get this done soon. If so, I might make it a kind of bonus thing that you can do during the exam period as well. So if you can solve a problem or two and kind of have it be a bonus. But if I don't get that done in the next couple of days, then I'll instead make it completely optional, where even doing it won't get you bonus points. So, I'll see whether I can post that soon and have it count as a small bonus if you do solve a problem or two. But otherwise, I'll make it completely optional. But in any case, it won't be a required part. So either way, it won't be required. So, all right, as a reminder, there is an anonymous feedback thread on Piazza. I encourage everybody to kind of leave me feedback for how this course was, anything that you feel like can be improved, or any feedback on the content, which parts you found more interesting or less interesting in terms of content, and the format as well. I guess it's a special case because, of course, it's an online course, but still, I would still like your feedback about how it worked as an online course and what parts can be improved in terms of the format of the course as well. All right, so with that, thank you very much for taking this course, and I look forward to reading your final project reports, and feel free to contact me about those as well if you have any questions, you want any more additional references or anything like that. So contact me either by email or preferably private notes on Piazza. I've actually missed a couple emails from students in the class because they kind of miss my inbox by being labeled as spam or by some filters I have on Gmail. So I really try to not have that happen, but it's happened. So I think Piazza is a little bit safer. So private posts on Piazza are the preferred way to go, but you're welcome to email me as well. All right. So thanks for a great course.
Yep. Thanks.
Thank
Bye.
you.
Thank you.
Thank you.
Bye, everyone.
Yeah, thank you.
All right.
Bye.
Bye.